HGeom0704. This is on regular polygons, and the hope is by the end of this section you can work efficiently at finding angles, both interior and exterior, of regular polygons. All right, starting up. Here we have 4 basic common regular polygons. Notice they all have 2 similar characteristics. That is, in each shape their angles are all congruent, and in each shape their sides are all congruent to each other. So what does it mean to be regular? Regular means same shape and the same size. Shape refers to the angle, and size refers to the lengths or the dimensions. Let's go lengths. All right. The only important rule that we're covering today is the each exterior angle theorem. I abbreviated each with EA. Hope that's okay. And here we have a polygon with 4 equal sides. And I've marked the exterior angle out here. And the rule says that if a polygon is regular, then each exterior angle is 360 divided by something. Now, if you stop and think about that, like 360 divided by what? Well, 360 is the sum of all of them. So if I were to extend each side again, there would be 5 of them. And so on a pentagon, I would take 360 divided by 5. And on an n-gon, I would take 360 divided by n. By the way, something to keep in mind, think about as you do problems. When they ask you to find the interior of the angle here, there are some students that say, well, you can do that, or you can actually find the exterior angle, then subtract from 180, because if you notice, they're supplementary. Number 2, this formula is easier to work with than n minus 2 times 180 divided by n, right? And given the choice, this one's simpler. So, in that is the case, let's move on. Here we have a pentagon, and it says find the exterior angle. Looks impossible because there's no numbers, but again, because it's a pentagon, means we've got 5 sides. So n is 5. And we know the sum is 360 because we're dealing with exterior angles. So 360 divided by 5 is 72. Okay, simple enough. Go ahead and do it for a regular heptagon. I will wait here while you find a heptagon the exterior angle. Again, n, sum, and then you're going to tell me the answer. All right, well, hopefully you got an answer of 51 and a messy part. What did you do with that messy part? Hopefully you said to yourself that some ratio over 7. Now, typically you don't want to round off answers, so always writing it in terms of 7 is good. So the question is, how much over 7 is that? One way to do that, to figure that out, is an easy way to figure that out, is take 51 times 7. And note that gets you 3 degrees away from 360. So therefore I know that it must be 3 that is the remainder. So 3/7 is the measure of the exterior angle. Okay? This problem, again, is exterior working backwards problem. If you know the exterior angle, then how do you get? Well, again, we set it up. 18 degrees is equal to 360 divided by something. Again, to solve this, multiply by n. So now we have 18n is equal to 360, and now divide by 18. Hopefully you don't need a calculator for that, and you merely say 20 sides. If somebody were to give me this problem, you could set it up as 108. Since they're working with the interior angle, you could say n minus 2 times 180 over n. Solve that for n. You could just also have this memorized, much like you have memorized families of the right triangles, Pythagoras. The other third alternative, or actually you don't have those yet memorized. We'll work on that in a future chapter. The other way is, I'm not going to mess with interior, I'm going to mess with exterior angles because the formulas are much easier there. So the exterior angle in this particular problem, 108 minus 180, or excuse me, the other way around, you get 72. Now if memory is working for you, you remember, oh yeah, we just did that problem, that's a pentagon. But if not, you just keep going on this problem, 72 degrees is equal to 360 over n. Solve that problem and you'll get n equals 5. Okay? So again, you can work on it directly, solve this problem, or work the backdoor technique and work with the exterior angle. Again, make sure you find the supplement and then use the supplement theorem. All right, last but not least, they give you a stop sign and they ask you, is this triangle scalene, isosceles, or equilateral? Hopefully you remember what those mean each. And in looking at this triangle, you should say, oh, well, it's definitely not equilateral. It's either scalene or isosceles, or maybe neither. You're suspicious that possibly this NT and NE are the same. And I think we can make an argument and say that those are, in effect, the same measurement. So our suspicion is it's isosceles. Why? Because we think NT equals NE. How do I know NT equals NE? Well, so glad you asked that question. I think here we have a trapezoid. I think here we have a trapezoid. And those two trapezoids are actually congruent trapezoids. We've never done a proof of congruent trapezoids, but I think you could argue that those two sides are the same. And those sides, being sides of a regular octagon, are the same. And I think from this point, you could create triangles if necessary, but you could then say, well, because those two trapezoids are all the same, and we know that these angles on the interior are equal to those angles, then these two trapezoids are fixed, and they are congruent to each other. Therefore, their bases must also be congruent to each other. So, isosceles is our indirect proof. Hopefully that lesson was not too long, and hopefully the problems take just as little time.